Okay, welcome everyone to this talk that I gave. Well, it's a recording of a talk that I gave in July 2024, which is not when I record this. In particular, it will not be when you watch this. But anyway, July 2024 is the past at this stage. I'm still giving the talk. I'm still trying to communicate some ideas here, which is somehow better if I do it here in my little studio. And they're actually part 1, 2, 3, 4, 5. Oh, it's a lot of them. 1, 2, 3, 4, 5. So there will be a lot of material to go. And this idea of the series of talks, of the lecture series, whatever you want to call it, that I gave on the analytic theory of monoidal categories. Yeah, or how I would call it, the strategies to avoid counting. Essentially, that's what it is. Whatever you well, we'll go into some details, but this is of course like more like philosophy or whatever. But there's something I would really like to communicate in these videos, and this is that as a young student, you always think like analysis, so analytic methods and algebraic methods are like really different, and they will never be able to talk to one another. And later in your life, you realize that they're actually exactly the same, and they're maybe not exploit as kind of a synergy as much as they should be, but they're really closely related. So analytic methods help a lot in algebraic topics, and the other way around is also true. So functional analysis is a classical example of where you have a lot of linear algebra topics for more in analytic theory. Okay, and now I kind of have something in mind. I'm trying to sell this story of whatever type of analytic theory is, whatever that means. I'm going to zoom in a little bit, but whatever that means, eventually it's actually helpful in a lot of algebraic or counting type problems. So whenever I say algebraic, I really mean counting type problems. It could be algebra, that could be in the study of category theory, or that could be in the combinatorics, graph theory, something where you would count. Okay, so let's get going here. So my first and kind of the key example, and I think even the historically first, I might be wrong because it has been around for a long time, but anyway, kind of the key example of how this is supposed to work is the prime number function. The prime number function, very easy, usually denoted pi. So it's not the pi, it's another pi. Anyway, so the prime number function, pi, is just a number of primes lower than a given bound. Not going to do that, it's too difficult to count, and that's the whole point. So this function is like difficult to count. Prime numbers are like random. So what actually do you do? They pop up randomly. So how can you even estimate, or how do you even get your hands on this function, which is arguably one of the most important functions in mathematics? I'm not quite sure why, but people tend to like prime numbers. So this function seems to be kind of important in mathematics, or it is important in mathematics. And people were kind of studying this function, and you kind of, the flavor I want to sell are 3 types of different questions you could ask and you can answer. Although the general question, how to write down that function in whatever, some nice polynomial form or something, has no good answer, right? You can still answer certain types of questions. And to do this, people invented analytic number theory. This is like kind of my selling point here. Analytic theory of monoidal categories, kind of analytic number theory. Motivated, just applied to a different field. Anyway, so the first type of question you might ask is, how does the function grow roughly? What is the leading growth of the function? And it's clearly bounded by n, because I'm counting the number of primes lower than n. But what is less clear is that it also grows like n. So it actually is not very far away from a growth like n, and you can see that here in my little log plots. So log plot mean I take a log on the y-axis, and in a log plot, a linear growth is a log. So here you see the different logs. So my bound n, and then the pi function is a blue one. So the bound n is a dotted one, and the pi function is a straight one. And you can see they kind of have the same type of slope. And that's what I mean by leading growth. It's still kind of a bit of an overshoot to just say n, but kind of the overall kind of slope of those pictures looks very similar. So the leading growth was determined, like people knew that very, very early on. And then you might wonder, can you actually do better? So this dotted curve here looks much better than the dashed one, the top one. So people were wondering, can you actually study something better? Can you? So this is kind of an easy type of question. Can you beef it up? Can you study something nicer? And people started doing, well, a long time ago. Nowadays you just do that on your phone, and it's like, bop, done. But it took a long time ago when people started to do this. They had those tables of prime numbers. So Legendre, for example, is a famous example. Legendre had this table of prime numbers. So the pi function up to 400,000, and it says per formula, given by the formula, and the counting per table, whatever, 1, 5, whatever, 1, 5, whatever it is. And the formula Legendre was guessing for pi n is this guy. So the famous n over log n. And then Legendre was still guessing that there is some correction factor, which looks pretty random to me. And yeah, this is like wrong, but it actually does really good on those first 400,000 examples. So that's what people did. And of course, Gauss claimed eventually, I've done that when I was 12, lying naked in my bed in the early morning after I was drunk the day before. As usual, Gauss just claimed I have done that before, and because it was Gauss, people believe that it is true. And in this case, actually, I think it is actually true. Anyway, so if I would do that, if I would claim just I was drunk the night before and I was lying in my bed still at 2 p.m., and then I came up with the prime number theorem, people should get a bit suspicious, but because it was Gauss, I guess it worked out. Anyway, you can already guess here somehow what the prime number theorem is supposed to be. As I said, people were trying to make it a bit nicer by adding a correction factor, but that doesn't really work. It just works very nicely on the first few examples. Anyway, the prime number theorem is now the following statement. The number that the function that we are trying to approximate is approximately n over log n. And what log you use doesn't really matter. So n over log n, where this symbol here means the ratio becomes arbitrarily good. So the ratio becomes arbitrarily good, and you can kind of see that here. It has some floor in the beginning, so pi over the log n over log n function, but then it goes to 1 like quickly. Let's say quickly. And actually, there's a little bit of a beef up. I hope you are the correct audience that I can still pull up my beef up here. So I really like this function. This is because simple and easy. Like the probability of finding a prime is something like log n, or 1 over log n. But you can make it a bit nicer. You get a bit of a better approximation, and this is this famous logarithmic integral. Whatever, just a logarithmic integral. And it gives you also an asymptotic expansion, but it's somehow doing a little bit better in some sense. Anyway, so question number 2 is then, okay, we can't write down that function, but maybe we can do a bit better than our naive approximation. So maybe we should just ask whether this asymptotic gets nice, whether I can find some nice asymptotic formula. And yeah, this is not a trivial theorem. So Gauss and Legendre were not able to prove it. Took quite some time to get proven, but it's proven by nowadays for a long time. It has actually many known proofs. It's a celebrated prime number theorem, arguably one of the most important theorems in all of mathematics. So the prime number theorem is this type of statement here. Whether you want it to with a logarithmic integral or with my favorite formula n over log n, a bit of matter of taste. But anyway, the asymptotic behavior of our prime counting function is really key theorem in all of mathematics. And again, kind of the point here is, who cares whether it's a key theorem, right? Who cares? Mathematicians are insane anyway. No, the point here is that you can't say anything about the function really, like precisely, but you can say something like in the large n limit if you take this idea of maybe we just want to know a nice asymptotic formula instead of a nice precise formula. And that's really the key idea here. And then people were wondering about the third type of question I want to sell, in particular Riemann, which is something I call the variance. I'll tell you in a second what that is. How good is actually the counting? Yeah. So if you think of like my blue thing as like the expected value, and this guy here, the pi, of course, as the real value, then kind of the quality of approximation should be captured by expected value, the difference between expected value and real value. In Riemann, in one of the most famous papers ever, kind of made a conjecture, if you want, or computed the difference. So in Riemann's notation, whatever Riemann calls f is essentially the pi. So f is equal to the logarithmic integral. Remember that so f is pi. I want pi minus the logarithmic integral, and I want kind of some nice formula for this one, which is what I call the variance. Anyway, so yeah, f is equal to pi, and so there should be some error term, and Riemann writes down an error term. And whatever that error term is, there's only one kind of most important contribution in some sense, comes from this little sum. And as Riemann writes, the sum is over a sum für alpha sämtliche positiven Wurzeln der Gleichung zeta equals 0. So the sum runs over all positive roots of the zeta function. And this is where this idea of all the roots of the zeta function are important comes into the game, because the error term essentially is determined by running over the roots of the zeta function. And that's why people are always like, hey, we want to kind of know where the non-trivial zeros of the Riemann zeta function is, right? Because it gives you the variance of the problem of counting the prime numbers. And yeah, so this is like the third type of question. Can you find the variance from the expected value, like the difference? And this is like really difficult. Yeah, so we're going up in difficulty here. Question 1, the overall growth rate, reasonably easy. Question 2, an asymptotic formula. Well, it's a prime number theorem. It's a bit difficult, but it's doable. Question 3, the variance is the Riemann hypothesis. Let me just say it out loud. The variance is given by the Riemann hypothesis, or something that is essentially equivalent to the Riemann hypothesis. And this is, of course, difficult. I would recommend not try to do it. Anyway, so if the Riemann hypothesis is true, you could, for example, show that this is bounded. This does really just mean it's bounded by square root of n times log n. So the whole function itself grows like n over log n, yeah, and the variance is actually of the order square root of n log n, and you can completely ignore the log, obviously, because log is log, so everyone ignores log. Log is gone, log is gone. So the overall growth is n, and the variance is square root of n, which is pretty shit actually. But anyway, here's one of my favorite formulas. You can be very precise. So there's a formula that involves pi and pi, if you ever want to do it. So it's the real pi and the other real pi. And it's this type of formula. Anyway, I hope you get the flavor here. Question 1, easy. Question 2, difficult, more difficult. Question 3, usually very difficult. And we're trying to answer like kind of type similar questions in the setting of monoidal categories. Right? That's kind of the idea. In the setting of representation theory, right? Analytic theory of monoidal categories, analytic number theory. It's kind of the motivation here in this game. I hope that makes some sense. And yeah, let's do the observation here. So precise results are very often out of reach. It's not just about counting prime numbers. Just think of all the real world sciences. They will never have really precise results. There's this famous p-value or something, maybe. And yeah, so approximations are usually much easier to get. Sometimes the only things you will ever get. And they still might give you beautiful results. Just the prime number theorem is just amazing. Like everyone likes the prime number theorem, I hope. And the idea is that this actually should work. These analytic methods, like finding approximations, should actually work in all counting areas. Discrete math and number theory, combinatorics, graph theory, category theory, whatever, you know. So we're trying to do the same. And this is the whole idea. And this is what we are going to do in these 5 lectures. We are trying to do the same in the intersection of representation theory and category theory which I will just call the study of monoidal categories. This was really shit. Which I will call the study of monoidal categories. Right? Monoidal categories, intersection of representation theory and category theory. And essentially the outline here is that I will do some motivating examples today, and then I will focus on certain problems and I will tell you something about it. It's a lot of fun, right? It's not very difficult. You of course need some background, but it's a lot of fun, and that's why we're doing it. The motivating examples are mostly self-contained. I just say that and I realize that this is a math video for a certain type of audience. They're clearly not self-contained, but they're certainly not as difficult to understand as other type of math videos are. You should know what a matrix is. What a matrix is usually good to know. Anyway, let me give you the first example, the not counting in graph theory. So prime numbers essentially appear randomly. So here's my little spiral of primes. And if you zoom out, it looks like a noise picture, right? Random. Don't try to spot any patterns. Random. That's the whole point about prime numbers, right? But still, we actually can observe patterns. That's the whole point of my story. If we give up on this idea of making everything 100% precise, if you want. So eventually you need to let go, because really the part of mathematics where you can formally prove a formula or something, that's usually the very easy part. Scientists, like biologists, they know why they never do that, because any real world problem is just beyond kind of this type of idea of that you can always write down a formal proof. And this is also true in mathematics. A lot of patterns that you can observe will be impossible to prove. Yeah, just think of the Riemann hypothesis. It's a pattern you observe, but everyone believes it's true. But you know, whenever you can prove it, please write me an email. I will steal your ideas and get a Fields Medal or something. Yeah? So not going to happen, obviously. Still, the idea is if you give up a little bit on what you want to do, yeah, you take a few steps back, maybe you get actually a nice answer, which is, in this case, we are doing mathematics, still provable, but maybe not like a spot-on formula, maybe like an asymptotic expansion or something. And in graph theory, you can very often, graph theory is one of my favorite examples in this case, do exactly the same thing. So a random graph works as follows, and essentially you should think of them as an average graph. So you have a certain number of vertices, whatever, 10, and for each pair of edges, you flip a coin whether you put in an edge or not. Huh? For every pair of vertices, you flip a coin whether you put in an edge or not. And you do the same, and they usually look like noise. So average graphs, so if you have a lot of vertices, graphs get pretty much insane and they mostly look like noise. So here what I usually like to do is here I can create a random graph. Here's the probability. So I coin flip and 20 vertices and usually get to pictures like this. So you can run that and hopefully it won't take too long. And there you get another one of them, and you get another one of them, and you get another one of them, and they mostly look like noise. And if I increase this to 200 or something, it is just, yeah, it doesn't even want to show it anymore. Maybe I will just go to 100. Yeah, beautiful. And we can do it again if you want. And it's just, yeah, what should I say? It's just, yeah, it's just noise. It's beautiful. Beautiful, I like this. And you might think, okay, if I decrease the probability to 10% to put an edge, it's still noise. Yeah, it's maybe less noisy, but it's still noise. Anyway, so kind of the same. So the idea people had a long time ago in graph theory is if most graphs are kind of ridiculously difficult or random in that sense, maybe we should actually change our strategies and apply this idea of having kind of analytic methods applied to graphs. And why do those graphs look so random? Well, because for every pair of vertices you flip an edge, so you will have way more edges than vertices, and that's why it's kind of, keep in mind that an average graph has way more vertices than edges. That's essentially the only thing you need to know for the following types of theorems. So let me just say that again. I would take this graph NP, n is the number of vertices, and usually we do this for large n, and p is the probability to put in an edge. Right? And asymptotically, most kind of very nice kind of patterns arise. Although a lot of questions are really, really difficult, and you can still do it asymptotically. And this is actually like really, really cool. And for example, almost all random graphs are connected. Why is that? I just told you they have a lot of edges. If something has a lot of edges, then the probability that it's connected is really high. So don't get fooled by small examples. Almost all graphs will be connected. And it's easy to show if you believe this mantra that everything has a lot of edges. So I ran it over a database of graphs up to a certain number of vertices. The database has a little bit of a flaw, but anyway, let's ignore that. The pattern here is pretty straightforward. Around 15, 16, 17, around 18 here, essentially everything is already connected anyway, right? So connected versus overall is essentially 100%. Most graphs have many edges. So the thing you can say about this total mass is that most things are actually connected. It's a non-trivial type of statement. And note here that the proof, even if I'm not really proving it, I'm just giving you an idea of proof, but to write down the formal proof is not difficult. You just need to believe this mantra that, like everything, most graphs have many edges. Just keep that fact in mind. It's kind of the mantra we want to do. Same for planar. Planar is a condition that is difficult to satisfy if you have many edges. So eventually, no graph should be planar, and that's exactly right. So something you can prove about this mess is that almost no graph is planar. Huh? So kind of the opposite of that type of statement. And you keep on going. Hamiltonian, almost all graph is Hamiltonian, because Hamiltonian is you would find a path in the graph that visits every vertex once. That is easy to satisfy if you have many edges. With contrast, Eulerian, almost no graph is Eulerian, because that's a property of finding a path that visits every vertex, every edge exactly once. That's difficult to satisfy if you have many edges, and exactly the correct pattern arises. Almost all graphs are Hamiltonian. And this is kind of really the first really exciting statement, because it's difficult to check whether a specific graph is Hamiltonian. It's a difficult problem. It's NP complete, as far as I remember. It's difficult, but almost all graphs are Hamiltonian. So somehow it's kind of a flavor you see all the time. There's some difficulty in a very tiny class of graphs, in this case, a difficulty in a very tiny class, and on average, everything is actually nice. And this idea of taking this limit and do some asymptotic approximation is really this idea of ignoring the bad cases. Yeah, you ignore the black sheeps, because almost all sheeps are white, and you actually get nice statements. Say it again. For a given graph to check that it's Hamiltonian, difficult. For a given graph to check that it's Hamiltonian with probability 1, easy. You just need to say, yes, it is. That's a very, very easy condition, very easy criteria. And this kind of shows the power of this approach. And you can go on. So random graph theory is like a very well studied field of mathematics. The automorphism group of a graph is almost always trivial. They have corresponding sequences, then it starts off very late, and whatever. The diameter of a graph just clusters in one point. The diameter of a graph is almost always true. Diameter is the maximal distance, and you can keep on going. The click number, something that is difficult to compute, is almost always concentrated in one value. It's like ridiculous. It's really ridiculous what you can say about them. And again, click number, very difficult to compute. But essentially all graphs have the same click number. Kind of interesting. And they're kind of the formula here, for example, depending on N and P. The number of colorings is concentrated essentially around this value here. It's just, and again, computing the number of colorings is like really difficult. So let me go back and explain these pictures. So I've computed 10,000 random graphs, and I listed the corresponding click number, and like whatever it is, 9,500-ish, whatever, have the same click number out of those 10,000 random graph on only 50 vertices. Yeah. Similar here. Here's a bit more difficult. Coloring is a bit more spread out. Essentially, it takes two peaks, but still there's a concentration going on. And again, checking for a graph, the number of colorings, if you want a precise answer, it's difficult. If you want an approximate answer, it's actually not so difficult. It's actually kind of really an exciting type of theorems, right? Summary, on average, an asymptotic might have nice answers even if the precise results are like really difficult. Yeah? So finding the chromatic number is NP hard. The fastest known algorithm is like shittily slow. Yeah, like really, really slow. But proving actually that most things kind of have the same number of colors is easy. And that's the type of strategy I would like to sell. That's the type of strategy I would like to apply in other parts of mathematics, in parts where you usually don't see these strategies, namely in category theory-ish. Yeah, I hope that makes some sense. I hope that's reasonably convincing. Even if the answer is really difficult to get usually, here, for example, in this example, it's NP hard, getting an approximate answer is still beautiful and usually much, much, much easier. And I think that's some of the old summary of what I'm going to do. Let me just show you 2 more examples and then I let you go. Like I can stop you just clicking from this video. But anyway, that's what I would usually say in a real lecture, and then I would let you go, because it's somehow much more difficult to sneak out a lecture, a real world lecture, than to click off a YouTube video. Anyway, not counting in algebra. So the GNU function is one of my favorite examples of not counting in algebra. Very similar to the pi function, it counts the number of groups of a given order. So as you learn very quickly, a GNU of a prime number, these are the red values here, is 1. There's only one group of that order. And then you learn essentially nothing more about it. And the reason is it gets really difficult. So maybe you have something like for p squared or something, or for p times q, but they're all just small examples, and just writing down anything about this function explicitly is really difficult. And what people usually do is they use a computer to kind of compute the number of groups of a given order. And this, of course, only gets you so far. But again, you can prove non-trivial facts about it if you give up on this idea of writing down the function very explicitly. So what is going on is the following type of idea. So if my favorite sequence, the first sequence in the online integer encyclopedia, the first one, the number of groups of order n, and if you plot that one, and you should definitely do a log plot, yeah, then it looks like a starry, starry night, showing exactly my slogan that everything here is, again, like random, right? It looks like really random. It looks like a starry, starry night. It's kind of, what on earth is going on? A pattern in the sea of randomness. So one pattern you can observe is, so this is a log plot of the first 1,000, and roughly here is an obvious peak, which is like higher than all others. Keep in mind that this is a log plot. This is much higher than all others. Yeah. And this happens to be, it's very easy to see, at 512. So it's this power of 2. And indeed, there are how many groups of order smaller than 1,000. And essentially all of them are of order 512. So that's a pattern you can observe. Kind of interesting. Anyway, determining this function precisely is difficult, but some patterns emerge if we again give up on this idea of making the count precise. And what you can do, for example, in this case, is you can write down an approximation of this function in exactly the same way as usual, and you can easily see that kind of the powers of 2 will be the most prominent ones, kind of picking out like the 512 with the corresponding number. So the number of groups of order p to the n grows like whatever it is, up to some correction term. So essentially it's a p to the cubed. P to the n roughly grows like p to the n cubed. That sounds strange. Maybe I should write GNU of p to the n roughly grows like p to the n. P to the n. Very good. Roughly grows like p to the n cubed. Yeah. So very fast, if you want. That's something you can prove. Non-trivial result, not too difficult, but non-trivial, while writing down anything more explicit about this group number function, there's not much known about it. Let's just say it how it is. There's not much known about the group number function. It's kind of the same type of flavor that we have seen before. And you might wonder, a ring generalizes a group, right? A ring generalizes a group because if you just you can have the corresponding group ring is a ring. So ring generalizes a group. And you might say there are probably much more rings than groups because rings generalize groups. Turns out that this is one of the wrong things to do, because kind of the group number order grows as, well, maybe I should be precise, 2 to the n cubed, and the number of rings doesn't do a much better job actually. So one of the many lies you're told, this is kind of where this asymptotic analysis actually becomes really powerful. So there are not many more rings than groups actually in this setting, because one of them grows like p to the 2n cubed and one of them grows like p to the 4n cubed. And then there's an over 27, which I'm ignoring here because it appears for both anyway. But yeah, so it's not much faster actually. So it's a little bit, yeah, sure, rings generalize groups because the group ring is a ring, but there are actually not that many more. And that happens actually very often, that you see a generalization, you know that people get very excited about it, but actually it's not much of a generalization in the sense of how many are there, because usually something is swamped by something, and in this case it's just the groups of order 2 to the n just swamp everything. So here's again our group number, now not in a log plot, and you can clearly see that almost everything is of order 500. So here's 512. Almost everything is of order the smallest power of 2 below 1000. Anyway, there was a lot of waffle. You could say a lot about this function without actually saying what kind of, you can't really write it down precisely, but we know next to nothing about it. But we know kind of the growth, for example. And this is kind of the type of idea I would like to apply in category theory and friends. This again, we'll have several more examples. The mantra is always the same. I hope you get this at this point. So something similar, abelian groups of order n. You can do the same thing, the eigenu function, and you can use the kind of corresponding picture. And you can say that the average number of abelian groups is kind of really funny. So there are a lot more groups than abelian groups. Yeah, the number of groups grows like hell. The number of abelian groups has an average that converges to a number. Yeah, and an average is just really just taking some of them all together and divide by n. Yeah, and that converges to a number. So there are not many groups, abelian groups of order n. Actually, there are on average 2.3 of them, which is a nice formula given as a product of the non-trivial evaluations of the Riemann-Zeta function on 2, 3, 4, 5, 6, whatever. Kind of very strange. So there, again, not many more. Sorry, this case it's the opposite. There are many more groups than abelian groups. Like many more. Yeah, the number of abelian groups is essentially constant if you want. It's kind of very strange. So if you draw out randomly a number, then there should be on average 3, let's say, abelian groups of that size. And this is something you can again prove, which is kind of one of those statements we are up for. Yeah. And just for comparison again, the number of semi-simple rings, that should generalize somewhat an abelian group if you want, and the number is essentially the same. Anyway, well, the average number is 2.5 instead of 2.3. Whatever. Anyway, I hope the pattern here is clear. There's something we want to know. We can't write it down. We really cannot. Yeah, no chance. But there are still cool results we can get asymptotically, or if you give up on precision. Here's another example. Character table of symmetric groups. Character table, kind of prototypical representation theory. And this is how it works. So here's another little character table. These are the simple representations. They correspond to rows. The irreducible representations. The conjugacy clauses correspond to columns. Yeah, class 1, 2, 3. Here's their size. Here's their order. Order really means for every element, what is the smallest, what is a good notion, what is the smallest thing such that they a to the t is 1, and that's constant on the conjugacy clause, so you can just write down the order. And forget those guys will not do them. They are the power maps. Anyway, so here's kind of the important information, and it encodes essentially the whole representation theory of groups in over the complex numbers. So you might ask questions about this table. So let's try to ask questions about the character table of a group. Okay, so here 2 more character tables. And you might wonder, so character tables are like not difficult to compute, and you might wonder how much information actually do they contain. Can I recover the group from a character table? And the first example you see is no, you can't. There's a group of order 8, this dihedral group of the dihedral group, the symmetry group of the square, D4, dihedral group of order 8, and there's this quaternion group, which have exactly the same character table, as you can see. Here, left and right, exactly the same picture, but the groups are not the same. So a character table does not determine groups. It's a fantastic thing to do, and essentially all of classical representation theory is about character tables, but they do not determine the group. So the question you might ask is, how good of a job do they actually do? How good are they? How good is the character table? And yeah, some patterns arise, and again, the flavor here I want to sell is the low number coincidence. So I've had to have a look at some patterns. So for Frobenius, abelian groups are determined by their characters. Yeah. Later, symmetric groups are determined by their characters. Later, roughly in the 1960s, non-abelian simple groups are determined by their characters. So a lot of groups are actually determined by their characters, meaning if you have a mystery group with a given character table, and you know that there's a character table of whatever a symmetric group, then your mystery group is a symmetric group, right? That's what I mean by determined by a character table. And yeah, so small number coincidences. A lot of groups actually, in some sense the important groups, if you want, the non-simple groups, are determined by their character table. But how do they do in general? How does a character table do in general? And I listed this plot. Here's the probability of things that are not determined by their character tables. And here's the order of I'm going through the groups of order whatever, up to 128, which is a power of 2. And you can clearly see what's going on. So everything is determined by their character tables. Then there is this group of order 8, the pair, and it drops down a bit, and then there comes the next prime power of 2, drops down a bit. Here's the next power of 2, the probability, then it kind of stabilizes, the next power of 2, and the next power of 2. So kind of the character table is doing really badly on groups of order 2 to the n. This is what this is saying, right? The probability of being not detected by their characters. It's kind of doing very badly on order groups of order 2 to the n. But a few minutes back, I told you essentially all groups of order 2 to the n. So probably the character table will do a pretty bad job. And yeah, so almost nothing is determined by their character tables. So people try to come up with a better way of doing it. So instead of asking, maybe the character table is not enough, maybe we should do some categorical things. And here's my first attempt of doing categorical things in this class. So maybe you could ask, does the representation category, not just its character table, which is like the Grothendieck ring, but the category itself, with all its structures as a monoidal category, determine the group? So, rep G equivalent to rep H, does it imply G is H? Note that this is always true, so this clearly checks, but the question is, does it work the other way around? Does the representation category determine the groups? And these groups are usually called categorically rigid. Yeah, categorically rigid. So how does it work? And low number coincidences, this is kind of a fun idea by Ettinghoff and Galacki, which is in 2024 when I was giving this talk, was 24 years old. But anyway, all groups that are determined by their characters are categorically rigid, obviously, but there are many more. All groups of orders congruent 1, 2, 3 mod 4 are categorically rigid. All groups of order smaller than 64 are categorically rigid. And this is pretty good result. It's kind of a low number type of coincidence again, because note here again that the powers of 2 are somewhat missing. So 64 is the first example where you find a group that is not, a pair of groups that are not categorically rigid. And that's usually dangerous. If something happens at all powers of 2, that's usually dangerous in the setting of groups. But what they were able to do is they were actually able to classify the groups that are determined by their characters, determined by their representation categories, which is like the original problem by Brouwer is, I don't know any answer to this, so it's probably very difficult, but this categorified problem with the monoidal, the category problem, actually works, which is a good selling point for category theory if you want. So the combinatorial problem, characters, you probably can't say much. Categorically, you can. You might now ask the question, how is this concept doing with respect to determining groups? I couldn't quite tell, so they don't say it in the paper, and I wasn't quite make out from the explicit determination, the explicit characterization, how many groups actually are not categorically rigid. I would suspect, even if someone proves me wrong, I'm super happy, but I would suspect that most groups are not categorically rigid. That's my guess. Anyway, so definitely it helped a lot, so it made it a bit better, and in particular you can exactly classify what groups are categorically rigid, and you would be, if you now sit down, you would be able to exactly tell whether something is determined or not. So whether this is a probability 1 thing or a probability 0 thing. Where here, in this easier problem, I actually don't know. I think nobody has done that ever. And I'm not sure whether this is easy to prove. That's why I call it a folk conjecture. Actually, you never find it written down anywhere. But here, it should be easy to work it out. I was just not able to do it. But you should get an answer, which is one of my selling points for categorification. Because now you've kind of taken a step upwards. Yeah. Here, this is a decategorified story if you want. Taking a step upwards, you have more structure, and you might be able to actually show it. Kind of an interesting problem in general. But I've waffled a lot, so let's come to the end of the video. The problem is checking this is difficult, and checking computing the character table is actually easy. So there's some other thing I'm kind of ignoring here, and this is a question definitely you want to ask at one point, is it actually worth the trouble? If you have something that is definitely better, but ridiculously hard, is it worth the trouble? Well, I will not answer that question for you, just putting it out here. Anyway, if you go one step further and you include the braiding, then you actually get that all groups are determined by their representation category plus braiding. But anyway, it's just an extra information. Anyway, this was what I was going to tell you about today, kind of a motivation of what we're going to see, kind of apply those types of strategies to the setting of categories. Anyway, I hope you enjoyed this video, and I also hope to see you next time.